So in this lecture, we are going to talk about testing and evaluation of insulating systems. So we have talked about certain concerns in designing the insulation, and we have also figured out what are the various mechanisms by which breakdown may progress inside a dielectric. What are the objectives of testing? We are aware that any apparatus that we used in power systems, if they are to be reliable, it will largely depend upon the insulation quality. If the insulation fails, the equipment, no matter how well designed it is, in other aspects is not going to be reliable. Materials, insulating materials that we use should have good insulating properties, and not only at a particular temperature, but over a wide range of operating parameters. Whatever parameters we expect will change in the field. The insulation has to have good dielectric properties over that entire range. And the only way to ensure that is testing. Testing can have three purposes depending on when you are doing the testing. Suppose you are a customer and you are going to buy an expensive equipment. Testing is the only way in which the customer can gauge the ability of the system or apparatus to meet the guaranteed specification of the dielectric properties. Now remember, we have discussed at length in insulation coordination that when we set the design, the design insulation level, we are not looking at zero failure. We are looking at certain probabilities of failure, certain acceptable functionalities, and these are given by the specifications. So the designer will design the equipment such that the insulation can withstand certain insulation levels, certain overvoltage levels, certain temperatures, certain field conditions. And when the customer asks for testing, demands testing, the customer is trying to gauge the ability of the system or the apparatus to meet this guaranteed specification. There is no guarantee that the insulation will not fail at any point or at any time or under any conditions. But whatever are the specifications to which the insulation has been designed, will those specifications be, will the insulation be able to withstand or satisfy those guaranteed specifications is what the customer tests. So that is from the point testing from the point of view of the customer. So every time a power apparatus is bought, we ask for certain test certificates. The manufacturer checks design. Whenever you go for a new design, there are certain tests which have to be performed, some on all the units, some on some of the units, to ensure that the design will serve the purpose. And lastly, testing is what the researcher resorts to in order to design a better insulation system, or to incorporate, to use a new material, to design a new material, to incorporate a new material into the design. So for research purposes, for design purposes, as well as for customer purposes, testing is of extreme importance. So therefore, we can look at the various kinds of tests that we are talking about. So high voltage testing can have two outcomes. One is acceptance and the other is design and research. So from the manufacturer or the customer's point of view, when an equipment passes a test, you are willing to accept it as properly designed. And that is essentially to see if the guaranteed specifications are being met. For design and research, of course, testing can be completely different, where you would perform various kinds of tests to ensure that you are going for a better system, either a better material or a better design. We must remember that since the different breakdown processes in different materials and under different test conditions are quite different, under different voltage conditions are quite different, the way that breakdown will happen when you have lightning over voltage, or where you have switching over voltage, or if it is under normal frequency over voltage, the breakdown mechanisms are quite different, and therefore there are different tests for AC, DC, and impulse tests. So passing the AC test does not guarantee performance under impulse testing. These will have to be done separately. So you have AC, DC, and impulse testing. Of course, under impulse testing you have lightning as well as switching testing. In certain cases it is enough to do a lightning test. In certain cases both are necessary. Apart from these, okay, high voltage testing can be of two categories, destructive and non-destructive. The most common kind of high voltage testing that we talk about is the disruptive discharge voltage test or the breakdown voltage test. Now, unless it's a gas, when you perform a breakdown test on a material, you are trying to see at what voltage or at what field breakdown happens. So you will actually have to allow the material to break down. For a gas, self-restoration of the insulation will happen. But for any other kind of material, the insulation is not going to be self-restoring. So this is a destructive test, and this destructive test is necessary. But you may also understand that destructive tests cannot be done all the time and to a very large extent. For example, every equipment which is to be commissioned cannot be made to go through a destructive test because it would destroy it. So therefore, we have to have some non-destructive tests, and non-destructive tests are generally geared at trying to estimate the change in properties, dielectric properties of your material, such that you can foretell or you can predict the life or the viability, the functionality of the system. We will talk about destructive and non-destructive tests later. Apart from that, there are three broad classifications of test, high voltage test. One is special, number two is type, and number three is routine. So what are these routine, type, and special tests? Routine tests are carried out. So here we are talking about standard tests. I will see what are the different kinds of standard tests. I mean, what kind of tests are standard. Routine tests are those which are carried out by the manufacturer on every unit produced. So you can well imagine that it must be a non-destructive test. An example of a routine test is a 1-minute power frequency voltage withstand test. So you have an insulation level for which your equipment has been designed, and this is the power frequency voltage. We also know that there will be some safety margin, there will be some protective margin. So actually you have designed for a higher insulation level, and the test will be performed at a lower insulation level where there is a very high chance of, high probability of withstand. But that will give you, if that minimum voltage is not withstood, that means there is either a problem with the design or with the manufacturer. So this kind of routine test are carried out by the manufacturer on every unit that is produced. Type tests are performed by the manufacturer on only a few samples. So these may be destructive or non-destructive. They're performed in a few samples to check the design. So when a few of the samples, and when I say few, how do we decide few? That is another question. But we are not going to perform this test on all the samples in hand. We will perform this test on a few samples, and we will take the performance of these samples to relate to the behavior of all the other samples in that batch. And then you might have some special tests which check insulation behavior under extreme conditions. For example, let's say nuclear conditions. These may not be required for all insulating materials or all insulation systems, but may be required for insulating systems which are going to be used under particular conditions. For example, when India built a power station, a base station in Antarctica, they also had to design power equipment, and the power equipment had to have insulation, which had to fail, which had to pass tests at cryogenic temperatures or at very low temperatures. So let us now discuss briefly some laboratory tests. The main characteristics of interest of an insulation is the disruptive discharge voltage. This is something that we have already discussed when we talked about insulation coordination, but let me quickly go through the material once more because this is pertinent to testing. We know that the physical processes which lead to breakdown of material can be very random, and therefore the same stress which is applied for different times or different stresses applied for same time may not always cause disruption, and therefore we cannot understand or analyze breakdown voltage, breakdown stress, breakdown tests with a particular value of the voltage. We have to consider the randomness of the physical process. So the randomness of the appearance of the discharge can be modeled by considering a large number of stress applications. So you have to have a large sample, so that many breakdown tests have to be performed out at the same voltage for a same time, because we have seen earlier that the breakdown stress is a function, or breakdown voltage is a function of time and stress. So you apply a particular voltage, what is the stress in the insulation and what is the time for which you are applying, both these will determine. From a very large number of tests performed on the same sample, okay, you cannot perform it on the same sample, but a similar sample, I mean identical sample, same voltage applied for same times, you build a data set. The data set, from the data set, you can calculate what is called the probability of failure. The probability of failure will be a function of time as well as stress. If a fraction p of a large number of discharges causes discharge, that gives the probability of failure, and Q, which is equal to 1 minus P, gives the probability of withstand. Now we do understand that this kind of random processes, if you plot the data plot the data, you will have a lot of statistical variation, and therefore statistical analysis is important to make sense of your data. It's very easy to perform these tests, but to analyze these data with proper statistical methods is of very crucial significance. So therefore we have to use statistical methods to analyze the results. Why? Let's say this is a research material. You have a new material that you think will be better and should be used in design. Let us call that the candidate material. We also have to have a reference material. A reference material is an insulating material which has been proven to be effective in practice. It cannot be another material that you just know. It has to be a material which is already in application, where it is already in vogue, it is being used in the field. So this is an about which you understand, you know, even if you do not understand exactly how the breakdown happens, you know a lot about the material, you have enough data about the material. So that should constitute your reference system. So you have to have a reference system, you have to have a candidate system, and then you have to have a large number of data for both the reference system as well as the candidate system. And then you have to use statistical analysis or statistical methods to determine if there are real differences between a candidate system and reference system. So let's say you apply a voltage, and your candidate system, let's say your candidate system is a novel insulating material. Let's say it's a nanodielectric. We haven't talked about what nanodielectrics are. Let's say it's a new class of material. You have a nanodielectric and you are using epoxy. And you think it's a good idea, it would be a good idea to use the nanodielectric instead of the epoxy in applications where you already use epoxy, maybe bushings. So if you apply a particular voltage, you expect the epoxy to, let's say, break down at 38 kV per centimeter. It is not essential that it is going to break down. At 38, it may break down at 50 kV per centimeter, whereas the nanodielectric you have designed, you expect that to break down at 50 kV per centimeter, but when you apply the voltage, it may break down at 30 kV per centimeter. Does that essentially mean that the nanodielectric is not better than the epoxy? You cannot come to this kind of a judgment. So what you have to do is you have to perform a large number of tests on both the materials, the candidate material and the reference material, and then you have to use statistical variation, statistical analysis to figure out if there are real differences between the candidate and the reference system. Normal amount of variation is an outcome which can be quantified by using statistical distribution. So we have to be aware that there will be some variation always in the outcome, and that has to be taken into account, and for that we use probability distributions. Using the probability distributions, we first categorize the insulating material and we can compare between two different materials. Also, what is possible is we can derive an extrapolation equation based on aging tests at a few stress levels, and then we can perform regression analysis to estimate life of the material or equipment. This third point I will come to later. Right now, let us go through the probability distribution aspect of statistical analysis. So let's say I have here four materials. Uh, there are four curves here. One is green, one is magenta, one is red, and the other is blue. As you can see, three of these, I have performed a statistical distribution and I have plotted them all, not with respect to with their actual values, but with their respect of their mean values. And I have normalized them with respect to the mu. So for every distribution which may have any values, I first find the mean value mu, and then if you remember the way we did in insulation coordination, we normalize the data with respect to the mean value for that distribution only. And I find that when I plot on the same curve, I find that three of these distributions, the red, the green, and the blue, have the same mean value mu equal to 0. Compared to this mu, the magenta curve has a mean mu which is -2. So these are normalized value with respect to the mean value at one of these materials. But what is different for all these distributions is the standard deviation. The standard deviation is very small from the pointed curve, which is red, which is very large for the blue curve, which is 5. For the green curve, it is 1, so somewhere in between. And for the magenta curve, it is the same. Okay, it is 0.5, which is somewhere between the red and the green. So the most probable outcome is given by the mean value. The standard deviation is a measure of the amount of variation which is possible. More the number of specimens tested, more reliable will be your distribution, more accurately will be the mean or the standard deviation estimated. We've also talked about confidence intervals, which gives us the bounds within which a population parameter value is likely to occur with a given probability. So as we have talked about, we may not be, if the mean value is 30 kV per centimeter, we may not be able to guarantee that breakdown will always happen at 30 kV per centimeter. But if we have a confidence interval of 95%, let's say, we will be able to say that with 95% probability, the breakdown values will lie between two values. One lower than the mean, maybe a mean plus minus 3 sigma. So we will be able to say that with this amount of confidence, we are able to say that the breakdown may not happen actually at 30 kV per centimeter, but it will happen at 30 kV per centimeter plus minus x value. So the confidence intervals will give me the bounds within which a population parameter, in this case breakdown strength, is likely to occur with a given probability. It depends upon where you take your confidence interval. So it is denoted by the width of the confidence interval. So that kind of the uncertainty reduces with the population size. These are all normal distributions which are given by a distribution like this, 1 by sigma root over 2 pi exponential minus x minus mu whole square by 2 sigma square. Now, if you look at these four distributions, which would you prefer? Which material would you prefer? Obviously, you would prefer the material. You will not prefer the material which is denoted by the magenta, because obviously it seems to have a lower mean value. So it has a high probability of failure at a lower breakdown value. So that is out of the question. So the magenta curve, that material is definitely not better. I mean, let's say out of these three, the green is the reference material, and I have three candidate materials: the magenta, the red, and the blue. The magenta I'm not going to choose because it has a lower disruptive discharge voltage. It is not going to suffice for my purpose. However, all these three have the same disruptive discharge voltage. Now, which will I choose? I have the green. Would I really like to go for the blue curve? It has a lower probability of failure at the mean value. Is that what I want? I don't. Because if you look at confidence intervals, in case of the red curve, you will find that most of the area under the curve will be between two values which are very close to each other. So I have a narrow peak. A narrow peak means lower standard deviation, and I have less variation from the mean value. So if I design for 30 kV centimeter, the chances of breakdown happening at a very low value of 10 kV per centimeter is less for the red curve, as well as the probability of withstand up to 60 kV per centimeter is also less. You might think that in that sense, the blue curve is better because it is more uncertain. So maybe there is always a chance, a higher chance. If you look here, let's say this is a very high value of the over voltage. The blue does have a chance of withstand, whereas the red probably has no chance of withstand. But that is okay. This certainty is better because if you are certain about the manner in which your material is going to behave, it is easier to design for it. So we would probably prefer the material that is signified by the red curve. Now, one thing I need to mention is that this is a normal distribution that we are using. But for lifetime and strength data, so that is what we are talking about, the strength of the material, the electrical strength of the material, or the lifetime, how long will the material be able to withstand a certain stress. These kinds of data, they are kind of extreme value data. And in this case, for such processes, we prefer not to use the normal distribution, but rather use distributions like the log normal or the Weibull probability distribution function. I'll talk about these later. So the normal distribution function may not meet by best choice of analysis, best choice for probability distribution function for analysis of breakdown strength or live data, and for that we might have to resort to other kinds of distributions. Of course, if you remember, for breakdown stress, we talk about cumulative density function rather than probability density function. So a more convenient form, or the normal distribution, or any kind of probability distribution, this here we are discussing for the normal distribution, is the cumulative distribution function, which is given by capital P voltage V, 1 by sigma root 2 pi integration minus infinity to plus infinity e to the power minus V50, or sigma whole square by 2 sigma square. So here what we are doing is, we are not really interested in the probability of failure at a particular voltage. We are interested in the probability of failure or probability of withstand at that voltage, which means we are interested in all the probabilities of failure at values below that level. So if you're talking about this 50%, it means that it does not mean that if you apply this particular voltage, whatever V50, you are going to have breakdown 50% of the time. It means that the material will not be able to withstand this voltage V50 50% of the time, which may mean that breakdown can happen at any voltage which is on this curve from 0 to up to this point. Actually, from minus infinity to up to this point. So there will be a 50% probability of failure at this particular voltage. As we have discussed before, if you're talking about flashover, then so suppose this curve that we have just discussed corresponds to the testing of a gap flashover, a gap which breaks down. V50 is called the critical flashover voltage. In practice, the voltage range over which the probability of flashover is distributed can be CFO plus minus 3 sigma, and in that case, we call CFO minus 3 sigma as the statistical withstand voltage, and CFO plus 3 sigma is known as the statistical flashover voltage. And we would like to have a distribution where the statistical withstand voltage has a very low probability, whereas statistical flashover voltage also has above it a very low probability. As we have seen, it can be defined as 0.13% and 0.2%. We have already defined that. We also have to talk about censoring, because when an experiment is performed, there are certain situations where we know that the test result is not dependable. One example could be, for example, when we are performing breakdown tests, let's say we are performing a breakdown test with rod plane gaps. often we find that breakdown happens at voltages much lower than expected. And often, most of the time, when we take out the material which has failed, we see that in that case, the puncture mark is not at the center of the where the rod is. If the rod is sitting on this insulating material and this marking, the puncture mark is not where the rod was, but it is at the edge of the rod. And that leads us to believe that those breakdowns are not happening because of breakdown strength of the material, but they're happening because there might be partial discharges at the edge, stress intensification at the edge, which is not a material property, but rather a artifact of the insulation of the electrode assembly. So if we use those experimental values, those data also to estimate the breakdown strength, we will get a much lower value than is true. And therefore, in such situations, we might like to remove those data from our analysis data, from the data that is to be analyzed. So when an experiment is performed and population parameters are estimated before all specimens have failed. So this is one example where failure occurs and we are removing some of the failures from the data. Or let's say we are performing 7 tests and let's say after 4 tests have been performed and 4 materials have failed, we say, okay, we are not going to perform the test further. We will censor the rest of the experiments and come to a judgment. Now, so this is called censoring, and this censoring, so we need to do censoring often enough in practical situations, but we cannot do censoring arbitrarily. So there will be some standards for which to tell us how the censoring of the data can also be done when we are not going to take into consideration all the specimen parameters into our analysis. The type of censoring depends on the nature of the experiment and the methodology that is used.